Is everything working okay? Can you hear me? No? Good, okay. I'll go home. Made it to the last session of the day, everyone. Well done. So, the cloud has made things quite easy for us as architects and engineers. It's now easier to deploy quickly. You can deploy apps and infrastructure in a couple of clicks or a couple of lines of code. And it's also easy to go global, so you can deploy around the world, several regions, again, very quickly. So there is also something else that's very easy. It is easy to spend money. It's easy to rake up bills. And I'm a consultant by trade, so I have a couple of things to think about with bills in general. So I need to make sure that my clients are well architected, they're getting value for money with their AWS spend. I have various sandboxes with Steamhouse, my employer. I need to make sure that they're not over-provisioned, I'm not running things that are just forgotten. And I've got my accounts as well. So I have an AWS organization somehow that has 12 accounts in it, and I am still counting. Not entirely sure how that's happened, but here we are. And this is my bank balance on the line, so I need to make sure I'm on top of that. Usually when you think about costs, it's usually something virtual machine related. So it's leaving something on, or an out-of-control scaling event. So if you look around on Reddit, pretty common eventualities. But it isn't always EC2. So there's many ways of generating unexpected expenses, and more so as more and more AWS services are coming out, especially the AI ones. So that's why I'm here today. I'm going to give you some tips and advice based on my experience. So if you're in a position you're thinking about cost optimization, you're thinking about FinOps, you'll have an attack plan. You'll know certain things you can use. I'm going to be talking about step functions today. Now, for those of you that never seen step functions before, just a quick explainer. So step functions is an orchestrator. You can create workflows using AWS API calls, and there's some third-party ones as well now. Integrates with over 220 AWS services, and you can use it for observability, process tracking, and error handling. Now, it's completely serverless, and you can express it as code if you want to, but you don't have to. There's an onboard visual editor as well that you can use to make them. And just quickly, there are two types of step functions. We'll be talking about standard ones today. If you do want to talk about express ones, come and grab me later on. So just briefly before we start, a little bit about me. I'm Damien. This QR code is me, so socials, blogs, everything like that. And also a link to the session resources as well. It's all in a GitHub repo from there. I'm an AWS consultant at Steamhouse with a background in data. So things like I've been a DBA, I've been a data engineer, a data ops engineer, whatever flavor of job was needed that week to fix the problem. Separately, I'm also the leader of AWS User Group Lancashire, and I'm an AWS community builder in the data category. So let's start with talking about data first. So I'm going to be talking about ingestion pipelines, but this is also helpful if you are designing an app that's pulling data from an external location. So fundamentally, with a data ingester, you will have a data source. So this might be a database or an API. It might be on-prem or in the cloud. You may own it, you may not. You'll also have a target, which is something that you do control. So that might be an object store, database, or a hard drive, something like that. And you want to get data from the source to the target, for which you will need an ingester. So this is the piece of code represented here by Lambda. It could be ECS, it could be Glue, it could be any number of things. But it handles authentication. It handles the parameters for the data you actually want, so it might be a date, and the actual transferal of data itself. So a typical pipeline looks like this. You'll give the ingester a date. It will use that date to make a request to the data source, store the data in memory, and then write it to S3. Now, this is fine for a lot of ingesters. They run once a day because the data's fine. It's not an issue to get it. But real life, sadly, is complicated, and this doesn't work for all pipelines. So there are situations where a pipeline runs multiple times on the same day with the same parameters. So a common one with this one is you may have a data source where the availability of the data you want is not fixed. So it might be 9 o'clock, it might be 10 o'clock, there might be a delay and it's 3 p.m., but you don't know, so you just have to keep asking. You may have a broken technical process where you have a function that's doing its own thing essentially and just constantly pinging the API and there's no observability to track it. Or it might be that it's a poor business process where this is just the accepted practice to query the API without checking the data. It's not really been thought about much as to what the downstream ramifications of that are. So in these situations, you have an ingester that's constantly running, using the same date and bringing back the same data. And this brings with it some problems. So first of all, the amount of lambdas you can call is not limitless. So once you get beyond the default's 1,000 concurrent executions, you can request an extension on that. But if you hit that limit, especially at scale, you'll start to get failures with the lambda requests. And you'll also get resource exhaustion, depending on how your infrastructure is set up. And you don't need to have that problem. Now, of course, you're also paying for this duplication. So once you've exhausted your 3 lambdas, you'll start paying for those. And if you're writing data to an S3 data lake, and that's versioned, which it likely will be, then you're paying for the version duplicates as well. You may also find you get issues with the data source. So depending on which source we're talking and how it's set, it might be that you start moving to a higher access tier. If you ingest over a certain amount of data, you'll start paying more for it. The flip side, you might find that your ability to get data is reduced, so you start to get throttled because of the amount of data you're pulling out. You might just get completely shut down, of course, as well. They might terminate your access, or if it's a database and you exhaust the amount of connections you get, you might actually kill the database entirely. So this is not an ideal situation, so how can we fix it? So we can introduce the idea of a choice state within step functions. So you'll give this some criteria, and then from an upstream event, which you'll see shortly, give it some JSON data to evaluate. Makes an evaluation, and then depending on the criteria you've set, it'll follow a particular path. So if we go back to the existing ETL, this is what it looked like before, and this is the newer version of that using the choice state. So we've got 2 things going on now. We've got a choice state, and above it, an S3 get action event. So what's going to happen here, we're still going to give the ingester a date, so we're still going to give it yesterday's date. But before we pass that to the ingester, we're going to use it to make a call to S3 and check what the response to that request is. And there's 2 possible situations here. And the step functions will handle this for us, by the way, so we can set variables within the step function, so it'll be able to create that path for us. If we run that data, let's say we run it this morning, 9 a.m., that data is not in S3 at all. So the request for the data fails because it's not there. So S3 returns a failure notification, including within it a 400 response. The choice state then gets that 400 response. Based on the parameters I've set, we'll trigger the Lambda function with the date that we passed it in the first place. So there's not really a change here. We're still seeing the same behavior that we had before. But where this changes is if we run it again a couple of hours later. So we got the data at 9 a.m. It's now 3:30. We're asking again. So this time, the data exists, and S3 will return a success notification, which this time will have a 200 response. So in response to that 200, the choice state will now, in this case, call an SNS notification. So that could be an email, Slack update, anything like that. That could be anything. But the important thing here is that the ingester isn't being run anymore, because we know we've already got the data from the upstream request. So now we enter a situation where we're going to start saving some money. So first of all, we're saving on compute because we're no longer constantly calling the ingester once we know we've got the data. And bearing in mind this ingester could take 5 minutes, it could be 15 minutes. If it's on ECS, it could be longer. These are potentially substantial amounts of time that we're saving. We're also saving on storage because we're not creating version copies anymore. And we're also hitting the data source less as well now. So again, depending on what we're talking, it could be that we're managing the amount of data we're requesting from it, so we're controlling the costs. Or if it's a database, we're controlling the amount of traffic that goes through that, which brings with it its own separate criteria and potential issues. It might be that your data isn't stored in S3, in which case you could also make calls to DynamoDB instead of S3, or make calls to RDS or Aurora, or even if your database exists outside of AWS, so it might be Azure, GCP, or it might be on-prem. Because fundamentally, even if you have a separate Lambda function to make that call, it's still going to be a faster request than triggering the ingester again. So next, I'm going to look at a different situation. So this is a situation I walked into a few years ago with a legacy process that began to fail. I'm going to be talking about ECS this time. It could be Lambda, but in this case it was ECS, it was containerized. And we had 3 tasks as part of this process. So they're all independent of each other. It took about 30 minutes each, was the average for it. The major requirement was that it had to be complete by a particular time of the day. So it was by 2 a.m. this needed to be complete. Otherwise, you had downstream processes dependent on it were going to have issues. So these were linked together in a chain. They've been running fine for absolutely years. No one had really had a need to look for them. Until one morning, get a failure on, in this case, task B. So now we've got a failed job, and we've also got a broken chain as well. So now we start to get a few issues. First of all, the on-call person gets woken up at 3 a.m. Secondly, the failure of task C, well, I mean, the state of task C, we don't actually know what state task C is in at the moment. Because if we briefly go back to task B, we know that that failed, we know the chain broke, but we don't actually know the status of task C. It may succeed, it may not. And then we've got the downstream processes as well. If for whatever reason this isn't fixed, we're going to have a bad time in a couple of hours when the business wakes up. And again, now we start to get costs. So immediately, there's an on-call cost. Best case scenario, it gets fixed during the on-call window, in which case I am now exhausted for the rest of the day, so you're getting very little out of me. My productivity tanks because I've been up since 3 a.m. trying to fix this, making sure everything else works. Worst case scenario, it's not fixed, it carries on to the morning. You get other people on the team, other business areas, all impacted by this problem. And ultimately, if your customers start to get impacted by this, you're getting complaints into the business, you're getting loss of revenue, and depending on what this process is, you may be looking at fines as well, depending if it's a regulatory process. So this was happening more often. We went back to the chain, tried to figure out what we could do to improve it. So on looking at the jobs, it was just organic growth. The business had grown to the point that what this was processing was outside its ability to process it. Also, these jobs didn't actually have to be chained together. They'd just been done like that by the engineer at the time, hadn't been looked at until now. So there were 2 changes made to it. First of all, put them on Fargate. And second, put them into a parallel state. That looks like this. So now each task runs in a separate pipeline, and they all start at the same time, as opposed to waiting for one to finish before the next one starts. Now, you can still have dependencies in this. So if there was a task D that depended on task B, you could still have them following each other, but they now exist in their own pipeline. So as well as that, whereas before, the duration of this process waited from the first job starting to the last job stopping, this now takes the length of the longest job in that chain. So if they all finish quicker, then this will scale down faster as well. Potentially, this process could be done in 30 minutes as opposed to the 90 it was taking. Now, this isn't to say that you won't get a failure on B. It may still have an issue. But tasks A and C are completely independent of that. So if I get a call out during the evening or at night and I log in, see what the problem is, I know straight away where my attention needs to go. Because, as you'll see in the demo later on, this is pretty close to what you see in step functions itself. So there's no longer a need to start looking through the logs, see where the problem is. You can immediately know what has worked, what hasn't, and where to focus your time. What you can also do is put retry and catch logic into the workflow too. So if you've got certain errors that are either fixable by remedial code or that aren't critical, that don't need to cause the failure of the job, you can put additional logic into your step function that will either trigger the Lambda function or the ECS task that will remediate that for you, or just flag that it's a warning and update the log accordingly. So now we start to see savings again. So first of all, the fact that all these jobs are kicking off at the same time, combined with the fact that everything's now running on Fargate, means that I can scale down to 0 faster than I could before. So I'm using less compute. And if the processes take even less time, if we alter the specs of the containers, potentially we can get that down even further with this modified setup. Because we've got processes that are fixing themselves, they're self-healing, we're spending less time on incident management, so the on-call costs are going down, and the business is more resilient. And the business now has additional time during the overnight process because we released an hour back to them because everything's parallelized now. So the business can use that extra hour for additional processes. So now let's look at the final aspect. This is a bit more of a well-trodden path, goes back to what I was saying before. So this involves using any service pretty much with the concept of a start and a stop API. So this example is going to revolve around Glue, which is AWS's ETL tool. But it also applies to any EC2-backed service, so that might include SageMaker notepads, it might include Amazon EMR, which is a more evolved, shall we say, version of Glue for higher distributed processing. And of course, EC2 itself, with the process of a start and stop for the instances. So this was on my accounts, this was with one of them. So this is my money we're saving now. And it goes back to last year when I was writing some blogs about Glue. And one day I noticed something on my costs in the AWS console. So a bit of context. This is AWS Cost Explorer. And these are my AWS costs for the first half of 2024. So there's a spike in February. That was around a workshop, so that was unexpected costs. You can see the first half of the year up to June was about $8, more or less. And the monthly spend, only about $1. It's only about a perfectly reasonable amount of money. So I'm writing these blogs. And then on the first 3 days of June, I almost spent $3 in the first 3 days. Got all kinds of cost usage alerts going off at me, and I immediately don't really know what's going on. So open Cost Explorer and see what we've got. So in Cost Explorer, you can break down to an API level to see what's actually creating these costs. That looks like this. We can start to factor in now and see what these actually are. So the red bar is tax. Can't do anything about that. The green bar is Glue's job run API. So I was running Glue jobs. There's no surprise there. So that leaves the blue bar, which is the surprise, and didn't know immediately what that was. And that turned out to be the Glue Interactive Sessions API, which, before we do any further digging, that's already the biggest cost indicator by far. So I know where to focus my time. So on a very high level, a Glue interactive session is a data preview tool, sorry. The idea being, if you're writing a Glue job, you are changing data. You're taking how it currently is and making it into something else. The way you would traditionally check that is to run the job and check the data yourself. But of course, that takes time, that takes money because you're costing the Glue jobs. So the idea of an interactive session is it will show you what the data looks like without having to actually run those processes. So it's supposed to save money, but clearly something's going wrong with what I'm doing. So what's happening? Had a look through the logs and figured out what I was doing. Firstly, this is part of Glue's interactive sessions interface. And you will see there is a stop button. Some of you may already know where this is going. So Glue sessions cost money while they run. And if they're not stopped, they do stop automatically. AWS capped them at 30 minutes. But these are EC2 backed, so that is 30 minutes that you're paying for. So this is the first problem. I'm forgetting to turn them off. And there's another problem. So what you've seen is the AWS console in the Glue session. So like most things, that runs in a browser tab. So having one tab open, got one session, which is one interactive session that I'm being billed for. Now, I have something of a habit, particularly if I get distracted, if I'm researching something, so as part of the blog post I was writing. So I will open a new tab, I will carry on, and I'll wonder why my CPU fan is going absolutely mental later in the day. And this is a problem with Glue sessions, of course, because if I'm opening a new tab, starting a new session, but I haven't stopped the one before, I've got increasing number of sessions, all of which are being billed for, all of which are running for 30 minutes. And we're starting to get an idea of what the problem is. So how do we fix this? What can we do? So going back to the end session button, I can't change the 30 minutes. That's hard-coded in the console. You can change it if you write them programmatically, but I'm using it in the AWS console. It's not an option open to me here. But this is an API call, and step functions make API calls. So I can use a wait state. And a wait state effectively does exactly what you might think. So it pauses the workflow for the time stated. Now, with a standard workflow, you don't pay for the duration of that wait. You only pay between transitions. So you'd only pay when the wait state ends and it goes to the next process. So this could be anything from 5 seconds up to a year is the longest time. So that looks like this in step functions. We're going to see a demo of this shortly. Each Glue session has a unique ID. So what I need to do is get that ID, pass it to this workflow, and let's say I've got a wait of 5 minutes. When that expires, it'll then stop the session and send an SMS notification. So there's some plumbing that needs to happen with that, which looks like this. So there's 3 parts here. In the first part, you've got a user interacting with Glue, creating the interactive session, the event for which is then sent to CloudTrail. In the second part, we've got EventBridge, which is looking for that CloudTrail event, sees it, pulls the ID out that I need, and passes it to the step function workflow. And then lastly, we've got the workflow that we saw before. Now, importantly, the stop request can fail. So there is additional retry logic in the stop request as well. If it fails, it's going to wait 10 seconds, and it's going to try again. You're going to see a demo of this soon. So what you're going to see here, you're going to see the step functions workflow. I have sped this up. And in the interest of time, I cut the wait down from 5 minutes to 30 seconds. Now, it turns out that that was a mistake, but it made for a good demo, so I left it in. And what you're going to see how step functions runs in real time. You're going to see the logs that get created, and then you're going to see the error handling as well. So you'll see there's nothing there at first, and then EventBridge sees the event and triggers the step function. So we've got a running invocation now. So we're going to see that the wait state is in blue, so that is happening now. We're going to see that the stop session event then turns orange. So it has failed, and it's going to retry. You can see down here as well, the logs are being created, and they're going to get created in real time while this is happening. So it being a pre-recorded demo, I already know this is going to fail again. And then on the third time, it's going to be successful. So the graph at the top will turn green shortly. Okay, so we've got a successful outcome. We can now look at the logs and we can actually start to unpick what's happened. So event 1 will show what the step function received. So we can see it got the Glue interactive session ID from EventBridge. If we then scroll down, we can unpick the reasons for the failures. So that's on rows 6 and 7. So we're going to see it tried to stop the job. And the reason it failed, it hadn't provisioned yet. So if something hasn't started, then it can't be stopped. And you'll find this with a lot of things. EC2 is another one with this. If it's not provisioned, it won't respond. This happens again 10 seconds later. And then on the third attempt, it's successful. So had we not had that retry in there, it would have failed once. I'd still have an interactive session running, and the step function would just have not tried any further. So go in with something like this, put the retries in. Did it work? That's always the important part. So this graph is only showing interactive sessions for the rest of 2024. So June's money is obviously spent, fair enough on that one. But importantly, for the rest of the year, there are no surprises. So the graph here is high because it's showing June's figures on the axis, but I'm only paying about $1.50 as opposed to the $3 I was spending in the June period. If you're interested, there's a detailed cost analysis in the session resources, so I've written about that separately. Now, stopping the session, not necessarily ideal, so there are other options. You could just do a notification or send a notification to another process. You could log access patterns, so if this is a team setting and you are controlling console access, you can monitor who is actually doing that, so you can either have conversations with them or remove their access. Or you can trigger an entirely separate process, so this could trigger a Lambda function, a container, something like that, that will perform additional processes if it detects a interactive sessions running after a period of time. So let's draw things to a close. We've looked at 3 different ways in which step functions can save money, both within AWS and outside it. We've spoken about how the choice state can reduce duplication and control data access and data costs. We've talked about how the parallel state can enable faster scaling to zero and bring resilience to legacy processes. And lastly, we've talked about how wait states can stop overrunning and forgotten processes and how they can save me from myself. So that's it from me. I've got the links from before here. So again, the repos, the articles, the documentation I've used to create this. So that's everything from me. Thanks very much for your time.
Thanks, Damien, for your talk. Do you have any questions? Show of hands.
I think we're kind of at that point in the day now where...
All right.
Brilliant, that's brilliant, yeah.
Wonderful. So in absence of any questions, can we give Damien a round of applause again?